So we're going to spend the next 15-20 minutes or so finish up this lecture. I know it says it has 97 slides, but I'm not going to cover all of it. I'm just going to get through the object-oriented part. Then I'm going to go over the final exam that will be given tomorrow at 3 o'clock. And then I'm going to go over the activity that you can do to earn extra points for the final exam, so you can fail the final exam and still do well in the class. And then we'll have some time for you to work on that special activity that you'll be doing. It's not really that special. But, anyway, so I'm going to finish up this lecture part first. So the lecture, I was talking about object-oriented databases and the concept of the differences between the object-oriented database and with the relational database model, comparing them. Ended by talking about the object IDs and how an object ID can be configured differently than a relational database primary key, and that the key constraints have a totally different concept to them as do object IDs. And then I stopped on this slide here for methods and messages, which are parts of objects, but they're not part of relational databases. So a relational database table that has attributes or data members, I should say, never has any of these methods. You can put methods into the table by creating stored procedures and other, add-on components if the database supports it, but we don't normally store a method or a message in there. By definition, the method defines the behavior of an object, the set of encapsulated functions. Think of them like functions. The messages are the requesting from one object to another. A message and a method really is the same thing for the most part. But a message, one object sends another message, a request to do something. Generally, it's to run one of its methods or to perform some operation on behalf of the other object. So objects showing attributes and methods as displayed in this picture here, we see the attributes are in the middle. This is about the same between the object-oriented databases and the relational databases. What's different are these methods. And so we have the four methods as an example out here that are surrounding, are part of the object definition or object creation. Here's an example of a method if you've never seen a method implemented before in a programming language. It is simply a function, and the function here is update salary. So it's a method that we can stick in the database so that when the object, as an example, a new record gets put in, or the employee, a new record for the employee, there's a raise or something given to the employee, we can run the update salary method and increase the salary of the particular student or particular member. So, and that would be not a stored procedure, but running as a method call. So, can we keep the volume down in the back of the room? Thank you. I'll let you just stop talking and everybody else realizes, oh, there's nothing going on right now? Yeah. Okay. So the class is the blueprint for defining a set. And then I start talking and then the volume, talking in the back starts again. All right. So, yeah, I can't tell you how rude that actually is. And I'm the one doing your grading, by the way. Oh, now it got real quiet. Okay, so I have to just mention the word exam, grades, and I'm the one grading, and you're being rude to me. And then all of a sudden, people start paying attention. Oh, really? Yes. Do you really want to do that? No. You want to be on my good side. All right, so a class is a blueprint for an object, as we know. And the blueprint is for defining a set of similar objects. And the object of a class is called an instance. This comes from object orientation. Everybody's familiar with this if you've ever programmed in an object-oriented language. We can use the same terminology with object-oriented databases. And if we do that, what we're looking at is making instances of objects instead of rows. Can you please keep it down in the back of the room or take the conversation outside? Thank you. I am the one doing your grading, by the way. So class instances share attributes and methods. And here is a class diagram where we have a class called, a class template called branch. Branch is broken out into two parts. We have the attributes and the methods. And then we have class instances that are created of this object, and the class instances are branch 005, branch 007, branch 003. For those of you who are here for the entity relationship diagramming lecture, the lecture that I gave you had some of these diagrams that looked like this, but they were for entity relationship modeling. The same book actually describes object-oriented modeling, and out of the same book, the same example from the entity relationship, which was the staff, the branch, if you remember this. Staff has branches, and there was something about newspapers and properties for rent for that example. Well, this might look a little familiar to you. It's the object-oriented version of that particular model. So we can take that same model. I'm not going to do it for this class, but we can take the same model that we did for the entity relationship diagramming and turn it into a class model, define classes, and then make instances of the classes. And then we're looking at something like this, where we have those branches and we have the locations and all of the information associated with each instance. And each instance is an object, and it's made from the class template, which is branch. So in object orientation, we also have the concept of subclasses and superclasses and inheritance, which we don't have in the relationship, in the entity relationship model or the relational database model. It's impossible to inherit one table from another table. The relationship doesn't exist. But if we want to express it, we can express it in terms of object orientation. It allows one class of objects to be defined as a special case or a more generalized case of another class of objects, which is the same thing that we're doing in object orientation, which is actually kind of interesting because once you've learned object orientation, apply it to databases, and then you have object-oriented databases for the most part. The theory is pretty much the same in terms of the implementation. So a special case are subclasses that are more general than superclasses, and processes of forming a subclass is a generalization, and forming of a subclass is also referred to as a superclass is a generalization. A subclass is a specialization in terms of the concept. And then the subclass inherits all the properties of its superclass and can be defined as its own unique properties. And subclasses are redefined as can be redefined as inheriting methods and data and everything that's above it from the superclass. So in the instances of a subclass are also instances of superclasses, and everything you learned about object orientation in terms of inheritance applies. You just take a table, and then now you can add more stuff to a table. So if you can inherit one table from another table, one object, if the tables are really objects from another object, and you're using inheritance, then that would sort of avoid the problem of having to actually join tables. So if you think of the concept, one of the most expensive routines that you're doing with SQL, with multiple tables, is joining them. And there's no relationship that's a hierarchical or in terms of the structure of the connection between any of those tables. And so normal standardized SQL being run on regular old relationship tables with joins, the most expensive, the least efficient way of actually running a query. In fact, you want to minimize the amount of joins that you do and then maximize the amount of keys and separate the data out so that you can essentially put it all back together using the SQL language. So imagine you didn't have to deal with any of that anymore, and instead you were inheriting one object from another object, and that object already had everything underneath it. Much faster, much more efficient. No more joins, so it's actually all together. The data is actually stored all together rather than being separately on an island of its own out there. So if you build a hierarchical relationship with the data by utilizing object orientation in terms of that hierarchy, you have the same reuse and the same advantage that you do in the programming language. So it's actually a really good selling point for actually switching over to object-oriented databases instead of using the relational model. Only problem is that's harder for people to understand. See, once people learn structured query language, and they learn the keys, the primary keys and the foreign keys, and they learn how to put everything together, that's easy. It's much easier to understand than trying to figure out, well, how do we take this object reference and turn it into that object so we can use it as a student table, and then turn it into this object over here for the registrations. And we have multiple lines of inheritance being supported, so we might have students and classes and teachers and schedules all put together. They'll come into this big other object called registrations, which abstractly makes a lot more sense if you think in an object-oriented way. But for a database person who may not necessarily be a programmer to work with that, the difficulty level is too high. So the big complaint that most people say about object-oriented databases is that they're very hard to understand. Well, yeah, you have to understand object orientation. So your average user not really going to even get past relational database concepts, who will struggle with SQL, maybe won't even learn that, isn't going to comprehend object orientation that easy. So long story short, we still don't have object-oriented databases on the market in the mainstream because number one, they're too difficult for people to understand. Number two, we don't have as much support for them because, well, from another perspective, actually I didn't mention this yet, but it just came to mind. It's real easy to program in an object-oriented language using an object-oriented database. It's not to go the other direction. So if you have a relational database or if you have an object-oriented database, both of them would probably work just fine in an object-oriented language. If you have a non-object-oriented language, like a procedural language, like PL as an example, your object-oriented database isn't going to work, but your relational database will. So you might say that the relational model is a little bit more flexible. It'll span across more than one kind of domain of programming languages. So it's basically a little bit more functional. So in terms of superclasses and subclasses and inheritance, the principle of substitutability, the state of the instance of the subclass, can be used whenever a method or a construct expects instances of the superclass. So basically that's changing the object references around so that you can reference classes in the same hierarchy that all belong to the same family, which gives it an added bonus in terms of the relational, except for the relational model. So the relationships between the subclasses and the superclasses, known as the kind of or is a or has a relationship, also holds true. So there's 4 types of inheritance: single, multiple, repeated, and selective. So in terms of the single inheritance, if we had a person's staff, and then staff was a manager or staff was a sales staff, we would have that supported one class to another. In terms of the multiple relationship, we could have a sales manager who's a manager and a sales staff all in one, which would be a good model support. And then the repeated inheritance, where we have a staff who's a manager and a sales staff, but he's also a sales manager. So we have a one class that goes into two classes that are going into one, and then we have one that's coming out of the two. So these are just different inheritance models that give you a variation on the implementations that have been going on. So in an object-oriented database, it depends on the implementation, which is actually kind of interesting. Because if you take object-oriented programming languages, for example, and you look at C++ versus Objective-C versus Java, you have 3 different implementations of the same concept. So you take and do the same thing with databases and have object-oriented database number 1 and number 2 and number 3. Well, you're going to have 3 different implementations of the same concept. So as the user, the database administrator, are you going to learn relational database design, which encompasses a lot more types of databases, or are you going to focus on one particular vendor and learn something like object orientation just for that vendor that's going to be completely different? So that's why, another reason why object-oriented databases hasn't really caught on to the mainstream as fast as it probably could have. It's not standard. There's no standardization in terms of its implementation. So there's no reuse of already, and there's no capital gain on any knowledge you may have picked up from working with one particular database. If you learn one database with the relational model, you've learned them all. In fact, this is an Oracle classroom where we're using MySQL. It's pretty much the same thing in terms of the database concept, but on an object-oriented, you can't really do the same thing. So until one leader is chosen out of the entire group of object-oriented databases, it's really going to be hard to actually even teach it from a formal education perspective, because which one are you going to pick? And then what are they going to learn? Are they going to learn something that's transferable to another database or out into industry? Probably not. So unfortunately, there's some standardization might actually help it. But the interesting thing is the relational model isn't standardized either. So we're working with something that hasn't been standardized traditionally. So when is it ever going to be standardized? Probably never. It doesn't need to be. So there's a lot of things out in the computing industry that aren't standardized, actually. TCP isn't standard. Actually, IP is getting standard. It's becoming standard, but TCP has never been part of any standardization, although it's used a lot with IP. In fact, that's how the internet's working. But internet protocols in general are standardized. So you can piggyback a non-standard on top of a standard as long as everybody's abiding by the same kind of theory, the same kind of movement, then everything works. So overriding, overloading, and polymorphism of object-oriented databases. To override is the process of redefining. To overload means you're going to complement, you're going to reuse a class, and you're going to have something span across multiple classes. And then polymorphism means many forms. So you have operations, inclusion, and parametric types of forms of polymorphism that might be capable. And examples of overriding might be a method in the staff class to increment the salary based on commission. And so then you can give a commission, create a method in the staff database table that's going to, well, I can't really call it a table, I'm going to call it an object instead, that's going to keep track of giving a commission versus giving a commission maybe for a manager. So you might wish to perform a different calculation for the manager. And it might not have anything to do with a commission. It might just have to be maybe the branch profits or something that can be incremented for that. So here's an overloaded print method as an example, where we have, in C++, actually this is, let's see, this is using printf. So to basically make different different calls to the same method using a different number or arrangement of parameters that works. Printing out integers and versus floats and stuff. Another interesting thing we can get with object-oriented databases is dynamic binding, which we don't get with relational databases. Relational databases are statically bound and statically compiled and statically everything, which is actually kind of funny. Every model runs that way. Nothing happens dynamically. Although data gets updated, it gets written. So we have this thing about the commit. We have this thing about the rollback and everything. Because we're essentially not binding things on the fly. Everything has to be committed, so it has to be saved, or it has to be unsaved, depending upon the terminology we want to use. So if we can create a truly dynamic environment, maybe in Java, there is a Java database, by the way, and it's object-oriented. So if we can implement that, we're going to do it dynamically, because we're going to take advantage of the Java runtime environment. We're going to take advantage of the process of selecting appropriate methods on objects given the instance that we're using, given the time that we're using it, and what we want to do with it. So with a list of consisting of arbitrary numbers of objects, as an example from the staff hierarchy, we could write, a list I.print or something, and then in runtime, we can determine which print is going to be invoked depending upon which reference to which object subtype we're actually using, which gives us a little bit more flexibility. We can't do that right now with a relational database. It just doesn't work the same way. Just like we can create complex data types that are composed, or even composition data types that are composed of other types or other subtypes, like an address. An address might have a street address, a city, a state, a zip. We can create complex objects that do a lot more. So the object itself can consist of sub-objects that might be viewed as single objects that are enclosed inside of the bigger. So the objects participate in a part of relationship. So it's not really an instance of, it's a part of. And then the contained objects can be encapsulated within the complex objects. Or you can have its own independent existence and its own object ID may be stored in as well to keep track of it. So storing objects in relational databases, well, that's an interesting concept. That's why object-oriented databases have evolved these days, the large binary objects. So Oracle supports that. So can you call yourself an object-oriented database when you're using tables and you're storing objects in fields and columns and tables? That's a loose interpretation of object orientation. I wouldn't call myself an object-oriented database if I was following relational database model. I'm not an object-oriented database. So truly, unless we're looking at an object-oriented implementation of Oracle, we're not looking at an object-oriented database yet. So one approach to achieving persistence with object-oriented programming languages is to use a relational database model as the underlying storage engine and then store the objects inside of the model. So requiring a mapping of class instances or objects to one or more rows distributed over one or more relations or tables. So to handle class hierarchies, you can have two basic tasks to perform. You can design the relations to represent a class hierarchy, or design how the objects will be accessed through the hierarchy itself. So you can actually implement an object-oriented database by creating the objects and sticking the objects inside of relational database tables. A loose interpretation of object orientation, but we actually have a couple of databases already in development. Not really quite mainstream, I can't remember their names right now. But there's a couple of researchers that have been creating this already, where it's using a relational model, but it's storing objects.
There's
So,
a framework called Hibernate.
yeah, Hibernate is one of them, that's what I was thinking of, that does exactly that. It's objects, but it's being stored in a relational model. So it's kind of a hybrid. Instead of taking the relational model and thinking of it from a relational perspective, I'm storing objects. The other way around, I'm working with objects and I'm using them, but I'm storing them in a relational to keep track of them for the persistent storage, but that's about it. I just pull it out of the table. In terms of storage, I don't think that's really efficient, but I'm not really quite sure what they've done in terms of, I don't know what the buy-in is for their methodology yet, so because I haven't really spent very much time with looking at that company, but that's one of them. There's actually two other ones that are doing something very similar to it. So storing objects in a relational database, we have the staff with the manager, salesperson, secretary, and then we have the relationship going on, and then this is the entity relationship model, but it's all stored in tables instead of being in an object form. So we can map classes to relations. So the number of strategies for mapping the classes to relations, although each results in a loss of semantic information. As I mentioned before, the class and the relation are sort of two different things. So the table and the class, they're not all storing the same information. So if you map from an object to an entity, or to a relation, which is another word for an entity or table, we're looking at a loss of the methods and a loss of the behaviors, but a retention of the data. If we go the opposite direction, we don't lose anything. So if we take a relational database and map it to an object, we don't lose anything because we didn't have any of those behaviors. So long story short, when you map it, you want to go from a relational table to object, because then you'll have less data loss, because you're going from something smaller to something bigger instead of something bigger to something smaller. So here's an example of a staff, a manager, a salesperson, and a secretary mapped backwards. So it's mapped from objects to tables. And if I take a look here, I see the same hierarchy and I can see the same mapping that would take place. But what I'm missing are the methods. Don't have the methods. So to map classes to relations, and this one here is mapping classes to relations with the map of the class or subclass to a relation. Here's the map of each subclass to a relation. We'd have to take each one of the subclasses that was in there and also create another relation out of it. Long story short, we end up with we should end up with an equal number of relations per objects, because each one of them would map to a one-to-one kind of scenario. But we might end up having a flatter, well, we're not going to have any hierarchy at all, so we're going to have a flatter structure, which is going to give us the appearance of there being more objects or more relations than there were objects. Because we're not going to take advantage of abstract classes or interfaces that are coming together to form into one object. Instead, we spread them all out. And then we have a whole series of tables, which actually, believe it or not, is what we do in the relational model, but nobody really cares about it because they think it's normal, and it ends up looking normal after a while. But really, there's a lot of tables when you're taking looking at, especially after you've mapped an entity relationship diagram and you've mapped it out into a bunch of tables. There's relationship tables and there's a bunch of other stuff that doesn't really even hold true, but it's retaining the relationships. Well, that creates a bunch of tables when you look at it, and it's all flat, no hierarchy to it. And so you look at that and you go, well, that's a lot of tables. And so people just start trying to hack away the tables at that point because they think there's too many tables. But sometimes those tables are needed. So here's kind of the synopsis here then in conclusion in terms of the next generation databases. The first generation was the network or the hierarchical database, and it did require complex programs for very simple queries, no SQL language, minimal data independence, and no widely accepted theoretical foundation. And then we got into that second generation. The second generation gave us the relational database model, helped overcome the problems of the first generation, added an SQL query language so that we could put the data back together and we can actually make meanings and associations with those data. And then the third generation is the object-oriented database management system that I've been talking about in this lecture. I'm going to give you the ideas of it. Only problem is there's no way of describing the model without giving you specific examples of how it was implemented. So it's kind of like taking the history of object orientation, or taking and explaining object orientation without using one single programming language. Because it's going to be a different explanation of object orientation if I'm talking about C++ or if I'm talking about Java or Objective-C. So here's the hierarchy going from the hierarchical to the network to the relational. And out of the relational, we got the entity relationship diagram model and the data model that's being used in a lot of software development, which is why this is sort of presented after relational, because relational gave us the model. And then we have the semantic data models that gave us object-oriented data models, object relational data models, which is different. The object relational data model is object orientation applied to relational database concepts. So object-oriented data model, at a minimum, it must satisfy database functionality, otherwise it's not really acting as a database. Has to support the object identity in order for the scheme to work, and provides encapsulation and supports objects with complex states. So we have multiple objects that can be enclosed inside of other objects. The origins of this come out of object-oriented research, traditional database systems. So we take all the features of traditional databases, we take all the semantic data models that deal with the object concepts, all the object-oriented programming techniques out there, the use of behaviors, the use of attributes, inheritance, polymorphism, encapsulation, all that stuff, put it in here too. And then special requirements to support the schema evolution of the database design. And then we're looking at the object-oriented data model, which the object-oriented data model works really well with object-oriented programming. Because when we store data and use data structures in object-oriented programming, what we're really doing is looking at the object-oriented data model. Take all the data in the program, separate them out by objects, create individual objects, and then we have model view controller that came out of that as a model view. Well, models the data, the view, and the three components, the events that occur on the data. So you take all of the different pieces and you separate out just the data, and you turn that into an object relational data model. And then you have relational data, you have an object-oriented relational database as an end result to that, which is where most of the research has come from on that. And it's really a persistent programming language, or a PPL, that is being used to manipulate the object-oriented or the object-relational-oriented model. So the language that provides users the ability to transparently preserve the data across different executions of the program, used by many different programs, many different scenarios. So in contrast, the database programming language SQL differs by its incorporation of the features beyond persistence. There's features in the persistent languages that are not supported in SQL. We don't have variables normally in SQL. We have substitution. We have the ability to use variables, but the language was never designed for that. Nor do we have control structures. You can't create a loop in SQL or use an if-then statement or something of that nature. And then beyond the capabilities, we also have transactions, transaction management, concurrency control, and recovery. Well, traditionally, SQL doesn't give us any transaction management, any concurrent control, or any recovery outside of a rollback that we get. But the language user, or the database programmer, has to create all these concepts on their own using SQL to come up with, what are we going to call a transaction? Here's this statement, this statement, this statement. Let me create some log files. Let me create some scripts. And you have to pretty much orchestrate everything manually for the most part. Where if you built it into a language, then you might actually be able to get a better implementation of it. Okay. In terms of, I'm going to skip the rest of this on the persistent programming language because we don't really need to know about that. But taking a look at the single level versus the two-level storage model, and then we get a multiple level storage model with object orientation. Traditional programming languages lack the built-in support for many of the database features, which is why we ended up coming up with a SQL language. SQL is a single level, as I mentioned before. It's a flat level. Everything's on the same level. We create a hierarchical object-oriented with inheritance model. We have multi-levels or two levels. So increasing number of applications now require functionality from both the database and the programming language. So if the language is hierarchical or multiple leveled, then if the database supports that as well, there's a closer match between the two. So they need to store and retrieve large amounts of data. They may be shared. They might be structured data. So the two-level model lends itself a little bit closer. So traditional, we have to decide on a traditional database management system. The program has to decide when to read and update objects, and when to write the code to translate between the application's object model and the data model that's used for the database. And then when to perform additional type checking in objects when an object is read back and forth from a database. And then also guarantee that the object itself will conform to its original type. And it's all manual effort. So difficulty is going to be happening, the manual effort, because of a conventional database. As a two-level storage model, we have the storage model with the memory, and then we have this database storage model on the disk. So it's referring to a separate kind of modeling system where it's not, I'm not talking about a hierarchy. What I'm talking about in this particular case is that we have the abstraction of the data, and then we have the data in terms of how it's being stored. Object-oriented database models give you the illusion of a single-level storage model with similar representation, so that the memory and the database, I don't want to yell at this. This is just ridiculous. I'll just wait for you guys to finish. Oh, one guy's still talking. He doesn't even know that I stopped talking, actually. Actually, he doesn't even know that I'm talking about him either. He's still talking, actually. Oy vey. Alright, I'm going to end this because I see there's no interest in this at all. So, at least there isn't from the back of the room. But anyway, so the two-level storage model here. If we could represent what is stored on the disk with what is stored in the memory and the use of the database, then we might actually be able to come up with a better representation from a programming language implementation. See, even when I talk louder, the guy is still talking. You're going to get an F in the class, by the way. Yeah, and you're still talking. He doesn't even know he's got an F already. I've given you an F. And the guy next to him raised his hand. He's like, hey, are you talking about us? Y'all have Fs. All right. Oh, now I got quiet. No, he's reading on a screen. He just still doesn't know I'm looking at him. You know, it's like when you go to the ballpark and you shine the camera on somebody and they're picking their nose. They don't know that the entire stadium is looking at them right now. He's still looking at the screen. So you told him I was talking about him. I already gave your grade out already. I don't care. You know, you don't have to study anymore or whatever it is you're doing. I'm sorry? Oh, I know he's helping him out, but he's causing a huge distraction, and you're the last row of the class. I know! I absolutely enjoyed that conversation I had with you when you didn't know I was talking about you. No problem, you already know your grades in the class. There's absolutely no reason for you to even be here anymore either, really, now that you failed. So. Oh, now it got real quiet. I don't want to fail. I don't want to fail. All right, so the rest of this lecture I'm actually not going, I wasn't planning on covering it anyway. It was on storage models. Don't necessarily need to get into this much detail about object-oriented storage models, considering the fact that it's not very standardized, and all of this has changed within the last couple of years. So, long story short, until we standardize the object-oriented models, we're not going to get any type of either format that's consistent in terms of storage levels or interpretation or representation in terms of how the data is actually being stored and used. But if we could come up with a more exact way of storing the data and representing it in terms of the memory that's being used, then we would definitely have a more stable approach to this. So the rest of this lecture actually goes through different storage models, object referencing, things of that nature. So hardware-based schemes and things, which, you know, it depends on whether or not you're going to develop your own proprietary hardware to support your database. I don't think anyone has really done that yet successfully, so, which is interesting. Alright, so that was essentially, and I think I have some conclusion slide at the end here, which is I'm going down to see. You're not responsible for the rest of this lecture, actually. I never covered anyway. It was kind of in this, and this was taken from the book that I was using for the entity relationship diagrams in the beginning of the course. So this is, about 100 slides, 97 slides of relational versus object-oriented information. There is actually kind of an interesting example, if you are curious towards the end, in terms of the object-oriented database design summary. And in terms of the summary, what we're looking at is the differences between the, and if we look at this slide here, we actually kind of see the big picture, actually. This is the end of, this is around 10 slides left on the lecture, so it's around slide 85. Where we have the object versus the entity, the attribute is the attribute, the association or the relationship. So relationship and association are pretty much the same. And then the message itself. Along with the instance versus the entity, entity types versus classes. So you can see there's a lot of similarity actually in the translation between relational and object-oriented design. In terms of the relations, we know about the one-to-one, the many, and all of the different combinations. And considering the cardinality that we're looking at, if we try to map that relationship between object A and object B, we basically just add a reference attribute for A, and then to maintain the referential integrity, we add it to B. Well, isn't that just a key? Well, it is. So we could put the keys in the database just the same way we use them in a relational model. So we're actually looking at a hybrid, if you think about it. Because normally models, relational models, objects in an object-oriented world don't worry about their relationships or their cardinality with other objects. But if you build it into the scheme, then one object can know that there's many of them that are involved with another object versus just one of them that's involved. So, which is actually kind of interesting for representing relationships. Adding a reference attribute to B and then containing a set of references in A. So you're adding information to the objects just the same way as you add information to the tables. So I'm not going to go through the rest of this because it's kind of tedious and way above and beyond the scope of this course. But I thought I would introduce the concept of entity relationship versus object orientation. Referential integrity, also important as well, for the same reason why we put it into relational databases. And we don't have any garbage collection, but we could put garbage collection in an object-oriented model. So, behavioral design, yeah, there really isn't anything outside of some details about the relational design and stuff like that as well. So, I'm going to stop this one. It's just the rest of, this was the conclusion of the lecture I started before we had our lunch break on object orientation. For those of you who are just now started paying attention, this was a continuation of the lecture that we had after, or just to say before the lunch break. So, and I'm going to